In this video, we will introduce our next application of the definite integral, which is calculating the length of a curve. So the idea is that if I have some function y equals f of x, its representation here is a graph, what is the length of this curve between a and b? Intuitively, what I'm thinking is that this blue curve is a string, and if I pull that string tight, how long is it going to be? That would be the length of the curve. Now I've indicated exactly what the formula is for the length of this curve. It's a definite integral from a to b of the square root of 1 plus f prime x quantity squared. And just to give you a small bit of intuition as to where something like this would come from, we do what we've done in the past. We say, well, if we want to determine the length of this, what we're going to do is approximate it. And we take this interval that we have and we break it up into a bunch of small little subintervals. And then on each subinterval, what we are going to do is approximate the length of the curve with a line. And then we add up the length of all of those lines. That gives us our approximation. We take the limit as n goes to infinity and it turns into a definite integral. And if we think about approximating the length of this small little segment, we might call this the length of sub I. So this would be corresponding to x sub I minus 1 x sub I. And the length, we would say, well, we might think of there as being a small little triangle here. And how the x values change would be the change in x. How the y values change would be change in y. So the length of this small little segment, and I should make that a change in y sub I and a delta x, would be the square root, so by the Pythagorean theorem, of delta x squared plus delta y sub I squared. And then if you think about pulling out basically a delta x squared, it pulls out as a delta x, but it also has to factor out of the second term in order for that to happen. And it's going to give you a 1 plus delta yi over delta x squared. And the idea is that when we see something like this change in y over change in x, we think dy dx. So we're really thinking of this quantity as becoming a derivative. And that gives you hopefully a small bit of intuition as to where this integration formula comes from. The important thing is going to be, can we apply this to a few examples? And in terms of that, let me make an observation that typically an integral of this form with the square root of a quantity, they're going to be very difficult to evaluate. So we're going to have to be very careful to pick specific examples in terms of our functions f so that this integral is something that will work out. And we will see in our next video several algebraic techniques that we are likely to encounter. Something else worth noting is that sometimes it's easier to think of something in terms of a function of y instead of a function of x. So if it's a function of y, it's the exact same idea. So you have some curve, x equals g of y, and you're varying from y values c to d, then the corresponding definite integral formula is exactly the same. It's just a g prime of y in here instead of an f prime of x. So let's find the length of the curve y equals x to the 3/2 from the point 1, 1 to 4, 8. So in terms of our previous formulas, what we're thinking is that we have the function y equals f of x, where f of x is x to the 3/2, and we want to find the length of this curve for 1 less than or equal to x less than or equal to 4. Because we're thinking about how the x values vary from the point 1, 1 to the point 4, 8. So in terms of the formula that we are going to use, the length of this curve is going to be the definite integral over how the x values vary, and we need to integrate the square root of 1 plus f prime x squared. So we just need to fill in the blank here in terms of what is f prime x squared. So f prime x is 3/2 x to the 1/2. So if we square f prime x, we get 3/2 squared, which is 9/4, and x to the 1/2, which is really square root x, squared, which is simply an x. So the length of this curve is a definite integral from 1 to 4 of the square root of 1 plus 9/4 x dx. And an integral of this form is familiar. It is something where we would want to use a substitution. What we see is this 1 plus 9/4 x inside the square root function. And if instead of having a 1 plus 9/4 x, we simply had square root u du, that would definitely be something we could evaluate. So I'm going to let u be 1 plus 9/4 x, so that du is 9/4 dx, and equivalently, if we multiply by 4/9, 4/9 du is dx. So we can now write the entire integrand solely in terms of this variable u. 1 plus 9/4 x is u, dx is 4/9 du. So 4/9 is a constant that pulls out front, and we have square root u du. But because it is a definite integral, we need to change our limits of integration, and to do so, we always use our substitution. That is what gives the relationship between x and u. So for the lower limit, if x is equal to 1, u is equal to 1 plus 9/4, which is 13/4. So our lower limit of integration is 13/4. For the upper limit of integration, when x is 4, u is equal to 1 plus 9/4 times 4, which is simply 10. So our upper limit of integration is the number 10. Now the resulting integral is going to be quite simple here because it's just a power of u. So recall square root u is really u to the 1/2. 1/2 plus 1 is 3/2. So what we get back is 4/9 times 1 over 3/2, which is 2/3, u to the 3/2 from 10 to 13/4. So 4/2 times 2/3 is 8/27. We plug in u equals 10, so 10 to the 3/2, and then we subtract away what we get when we plug in 13/4. So 13/4 to the 3/2. And since there are no quick, easy simplifications, I will leave my number or my solution exactly in this form.